Welcome to lecture number 14. In the previous lecture I studied the forgetful functor that goes from the global equivariant stable homotopy category to the G equivariant stable homotopy category for some fixed compact Lie group G. This forgetful functor arises from a homotopical functor, so it descends directly to the homotopy category. It is an exact functor of triangulated categories, it preserves infinite coproducts, and it preserves infinite products. Brown representability then implied that this functor has both adjoint, it has a left adjoint and a right adjoint. We also got a better feeling for the left adjoint by identifying what it does on equivariant suspension spectra. So if you start with the G equivariant suspension spectrum of a G space A and you apply the left adjoint, then you get an unreduced suspension spectrum of a global space that is a certain relative version of the global classifying space. You have to choose a faithful G representation V, and then you take this orthogonal space co-equalized with the G space A. The special case is where the G space is in orbit, it's G mod H, and then we get that the left adjoint takes the suspension spectrum of G mod H to the unreduced suspension spectrum of a global classifying space of H. In the generality of arbitrary compact Lie groups, the adjoints are not fully faithful. But we also discussed that in the special case, where we restrict all the way down to the non-equivariant stable homotopy category, then both adjoints are actually fully faithful. So this can be interpreted as saying that the non-equivariant stable homotopy category sits inside of the global stable homotopy category in two extreme ways. So in one way on the very left and in one way on the very right. Because we already have two faithful copies of the non-equivariant stable homotopy category inside of the global stable homotopy category, one should not think of the non-equivariant stable homotopy category as a subcategory of the global homotopy category, but rather it's actually a localization. You have to invert all those morphisms which are non-equivariant pi star isomorphisms. Today I want to look at the two adjoints in this extreme case down to the non-equivariant stable homotopy category in more detail. After all, the spectra, the global stable homotopy types that are in the images of these two adjoints are important and they have special properties. Before I go into this, I would like to give a slightly different interpretation of the left adjoint. So the starting point for this description is the fact that the homotopy category of every stable model category is in a natural way tensored over the non-equivariant stable homotopy category. So the homotopy category has a preferred action, for which I write smash in suggestive notation, which is a functor on the homotopy category of C cross the non-equivariant stable homotopy category back to the homotopy category of C. And this action is associative and unital with respect to the smash product on the non-equivariant stable homotopy category. Here's a reference where this tensoring is constructed with the use of the so-called stable framings, which is a stable refinement or stable analog of the framings by co-simplicial or simplicial objects. And then the claim is that the left adjoint to this forgetful functor, Lx, is naturally isomorphic to the action on the global sphere spectrum, smash. So this is supposed to indicate that we think of the sphere spectrum as this global stable homotopy type. After all, on the point Z level, the sphere spectrum represents both the unit here and the unit here, so I want to emphasize that this is a global homotopy type. X is a non-equivariant homotopy type, so this is for all X in the non-equivariant stable homotopy category. And this is referring to this canonical tensoring. You can act with a non-equivariant spectrum on something in any stable model category. So here's a hint of how you show this isomorphism. You first construct a natural transformation using the adjointness property. In one of the two directions. So for example, from Lx to global sphere spectrum smashed x, and you observe that the class of all x for which this is an isomorphism is a localizing subcategory. Of the non-equivariant stable homotopy category, and it contains the spherical spectrum. So why is it first of all a triangulated subcategory? That's basically because both of these are exact functors in X. Why is it closed under infinite sums? That's because this is a left adjoint, this preserves products, and smashing with a fixed object is also a left adjoint, so this also preserves infinite co-products. And the fact that the sphere spectrum is in there is something that I showed last time. If you apply the left adjoint to the non-equivariant sphere spectrum, you get the global sphere spectrum. So this is one way of how you can think of the left adjoint. It just acts by a non-equivariant stable homotopy type on a global stable homotopy type. There's also an infinity categorical version. And this hinges on the fact that every presentable stable infinity category supports the infinity categorical analog of such an action. So now this pairing goes from the infinity category across script SP, which is a notation for the infinity category of spectra, back to C. And again, this action is associative and unital with respect to the infinity categorical smash product on the infinity category of spectra. This infinity categorical version is a little bit better than the triangulated category version, because here this tensoring this action on spectra on C is actually even unique, well, of course, up to contractible shocks. And then the infinity category version of the L, so let me just write L infinity for this, of X is naturally equivalent also to global sphere spectrum and then smashed acted upon on X. Here's a reference for this infinity categorical property. The global stable homotopy types in the images of the two adjoints have special properties, and I would like to introduce terminology so it's easier to refer to them. I call an orthogonal spectrum left or right induced. If it's in the essential image of the left or the right adjoint. So the image up to isomorphism in the first case of the left adjoint from the non-equivariant stable homotopy category to the global stable homotopy category, or in the other case an image of the right adjoint. We can make this a little bit more concrete by just using the adjunction bijections. So equivalently, A is left induced if and only if for all y in the global stable homotopy category, the forgetful functor induces a bijection from morphisms in the global stable homotopy category from A to Y into morphisms in the non-equivariant stable homotopy category from UA into Qy, and then the dual statement, A is right induced if and only if the opposite property holds for all y in the global stable homotopy category. The forgetful functor induces a bijection and now y into A. Two morphisms in the non-equivariant stable homotopy category from Uy into Ua. So this is a statement that doesn't directly refer to the adjoints, but only to the forgetful functor. I would like to discuss these two classes in more detail, and I will start with the left adjoint. For the left adjoint, there is a convenient criterion that characterizes left-induced spectra in terms of geometric fixed-point homotopy groups. So an orthogonal spectrum A is left-induced if and only if it has, and now let me first formulate this as a slogan, if it has constant geometric fixed points. What do I mean by this? Well, the geometric fixed points are isomorphic to each other, and they're isomorphic to the underlying non-equivariant stable homotopy groups independent of the compact Lie group G via a specific map. So what I mean more precisely is, i.e. for every compact Lie group G, the composite start with the non-equivariant stable homotopy groups of A. Then I use the inflation homomorphism along the unique group homomorphism that I call PG from G to the trivial group. This inflation homomorphism gets us to the genuine equivariant homotopy groups of A. And then I use the geometric fixed point homomorphism to get down to the geometric fixed point homotopy groups of A. And having constant geometric fixed points rigorously means that this composite is always an isomorphism of graded abelian groups. So with a little bit more work, one can realize the geometric fixed point homotopy groups as a non-equivariant homotopy groups of a certain geometric fixed point functor. I'd actually already done this a couple of lectures ago, and you can realize this map on non-equivariant homotopy groups by a natural transformation of spectra, and then you could equivalently say that this specific morphism of non-equivariant spectra from the underlying spectrum of A to the G geometric fixed point spectrum is a non-equivariant stable equivalence for all compact Lie groups. That's what it means to have constant geometric fixed points. We want to show an if and only if statement, so there's two directions. Let me start with this implication, i.e. that every left-induced spectrum has constant geometric fixed points. So this means that we have to show that for all non-equivariant spectra, for all X in the non-equivariant stable homotopy category, in all compact Lie groups G, the morphism we've constructed previously from the non-equivariant stable homotopy groups of X to the G geometric fixed point homotopy groups of Lx is an isomorphism. We use an argument that we've used a bunch of times before. We consider the class of all X for which the map is an isomorphism and investigate its closure properties. So the class X of all X in the non-equivariant stable homotopy category for which these maps for all compact Lie groups are isomorphisms is a triangulated subcategory of the non-equivariant stable homotopy category. Why is this? Well, on this side, a distinguished triangle in the non-equivariant stable homotopy category goes to a long exact sequence of homotopy groups. On this side, we're first applying L, which is an exact functor, so it takes distinguished triangles to distinguished triangles. And then we're taking geometric fixed point homotopy groups for some group, and that also produces long exact sequences. So this is just an instance of the 5 lemma, but of course we have to check that the long exact sequences are compatible. And this comes down to the fact that this map is compatible with the connecting homomorphisms on both sides. But this again, if we go back to how those were defined, that the connecting homomorphisms have two components, the suspension isomorphism on the one hand side, and then a map induced by a projection from a mapping cone to the suspension. These are natural transformations, and all the constructions on the board, in particular geometric fixed points, commutes with suspension, and it commutes with mapping cones, because fixed points for spaces commutes with smashing with a space with trivial action and with the formation of mapping cones. So that shows that the two long exact sequences are really compatible, that you get on both sides for distinguished triangles, and hence this class is closed under 2 out of 3 in distinguished triangles. But also the class of X is closed under coproducts. Of course, arbitrary coproducts. But that's even easier, because on this side, non-equivariant homotopy groups take coproducts to direct sums, and the same is true for geometric fixed point homotopy groups. L first preserves coproducts, and geometric fixed points also take wedges to direct sums. So the class of those X for which this is an isomorphism is closed under infinite coproducts. And now we conclude that the class X is a localizing subcategory. That's what these two things together mean. Is a localizing subcategory of SH, and it contains the sphere spectrum. Well, because here we get the non-equivariant stable stems and non-equivariant stable homotopy groups of spheres, and that's the same what we're getting here too, because the left adjoint takes the sphere spectrum to the global sphere spectrum, and the G-equivariant homotopy fixed point groups of the G sphere spectrum are also just a copy of the non-equivariant stable homotopy groups of spheres. So we have a localizing subcategory that contains the generator of the non-equivariant stable homotopy category, so we conclude that X is all of the non-equivariant stable homotopy category. This concludes the proof that every left-induced orthogonal spectrum has constant geometric fixed points. And now we have to attack the converse. So that's this direction. Now we consider an orthogonal spectrum that has constant geometric fixed points. So let A be an orthogonal spectrum considered as a global stable homotopy type with constant geometric fixed points. Then we consider the co-unit of the adjunction. Let epsilon from, well, we first forget down from the global spectrum to a non-equivariant spectrum, and then we take the left adjoint. So this is a left-induced spectrum, and we have a natural map that compares this to the given candidate for being left-adjoint, the co-unit of the adjunction. Now we check what this co-unit of the adjunction does on geometric fixed point homotopy groups. So we get a commutative square. So here we have the non-equivariant homotopy groups of LUA going via the map under consideration to the G geometric fixed point homotopy groups of LUA. And these maps are clearly natural, so this goes by epsilon lower star to the non-equivariant homotopy groups of A, and this goes via an instance of the same map to the G-equivariant geometric fixed point homotopy groups of A. And here we have epsilon lower star. This diagram commutes, and now lots of these maps are actually isomorphisms. So first of all, the Left adjoint to the forgetful functor is also right inverse to the forgetful functor. So if we applied U again to this map, we get a non-equivariant stable equivalence, and that means that this map is an isomorphism. This is a left-induced stable homotopy type, and in the first part we showed that this has constant geometric fixed point homotopy groups, so the map on top is an isomorphism. And for A we have assumed that it has constant geometric fixed point homotopy groups. So this map is an isomorphism. And then as usual, a commutative square in which 3 of the maps are isomorphisms implies that the fourth one is an isomorphism. So this means that epsilon induces isomorphisms on geometric fixed point homotopy groups. And this is one of the ways of how we can test global equivalences. We can test either on genuine homotopy groups or on geometric fixed point homotopy groups. So epsilon is a global equivalence. So that means that our given A is isomorphic to something left-induced, and of course left-induced was closed by definition, the class closed under isomorphisms, so A is left-induced. And that's the end of the proof. Let us now turn to right-induced global homotopy types. The slogan here is that right-induced spectra represent global Borel cohomology theories. This needs to be explained. So if you have a topological group acting on some space A, and you have a non-equivariant cohomology theory, there's always the so-called Borel cohomology theory, which is just the non-equivariant cohomology theory applied to the homotopy orbit construction. And the right-induced stable homotopy type are global objects which encompass all these Borel cohomology theories for all compact Lie groups at the same time. In a little bit more detail, so if X is an orthogonal spectrum, G a compact Lie group, and A G space, then we need the G equivariant X cohomology of A. And that's the following group. X, an integer degree k, G equivariant of A, is by definition morphisms and the G equivariant stable homotopy category from the unreduced suspension spectrum of A into the underlying G spectrum of X shifted by K in the triangulated structure. So for this definition, we wouldn't even need a global homotopy type. It would be enough to have an orthogonal G spectrum. We could define this. This is a contravariant functor in A to abelian groups, and it sends mapping cone sequences in A to long exact sequences, and it sends coproducts in A to products. So this is an equivariant cohomology theory in the variable A. It's also functorial in the X variable. As I said, so this would work even if we had a general orthogonal G spectrum, but in the global context we have the adjunction that we discussed last time, and that gives us an isomorphism to the unreduced suspension spectrum of L V blank cross over G with A into X shifted by K. Here's the theorem that characterizes right-induced global homotopy types. An orthogonal spectrum X is right-induced if and only if for all compact Lie groups G and all G spaces A from the G equivariant X cohomology of A to the G equivariant cohomology of EG cross A. So EG is a universal G-free GCW complex whose underlying space is contractible. This has the diagonal action. And which map am I taking? Induced by the projection from EG cross A to the second factor is an isomorphism. Of graded abelian groups. And moreover, if this happens, if X is right induced, then the X cohomology G equivariant of A is naturally isomorphic in A and in X to the Borel cohomology, to the cohomology, but non-equivariant. There's no group here of the Borel construction, EG cross G with A. Okay, let's prove this. I will start with the second claim, so I will consider a right-induced orthogonal spectrum and show this isomorphism between the G equivariant X cohomology of A and the non-equivariant cohomology of the Borel construction. So right-induced means it comes from a non-equivariant spectrum, so let Y be an object in the non-equivariant stable homotopy category. So then we induce it up by the right adjoint, and we consider, let me just do this in degree 0, general integer degree is similar of A. So either by definition or by this isomorphism, this bijects with morphisms in the global stable homotopy category from the unreduced suspension spectrum of L V blank cross over GA, where V is some chosen faithful G representation, into Ry. Now we're mapping into a right adjoint, so we can use the adjunction bijection. And this is isomorphic to morphisms in the non-equivariant stable homotopy category from the underlying homotopy type represented by sigma infinity plus L of V blank cross over GA into the non-equivariant spectrum. The underlying functor commutes with suspension spectra, and this is an orthogonal space, an unstable global homotopy type. It's actually closed, the structure maps are closed embeddings, so we can get at its non-equivariant homotopy type by plugging in R infinity into the free variable. So this is the same as morphisms in the non-equivariant stable homotopy category from the unreduced suspension spectrum of L, V, R infinity. So this is a G space with a G action coming from the action on the faithful representation, cross over G with A into Y. But this is just a particular model for EG. It admits a GCW structure, it's non-equivariantly contractible, and the G action is free because the G action on V was faithful, so this is an EG. So in other words, this is really the non-equivariant cohomology of the Borel construction. So this is the construction of the natural isomorphism, which is in the moreover part. And now I still have to establish the equivalence of the two criteria. It remains to show that an orthogonal spectrum is right induced if and only if the projection from EG cross A to A induces an isomorphism in G equivariant cohomology. So we let A be a G space, and we observe that when the projection to the second two factors from EG cross A to EG cross A, which projects away from the first factor, is a G equivariant homotopy equivalence. After all, EG cross EG is another universal weakly contractible G space, so the projection of EG cross EG to one factor is a G equivariant homotopy equivalence. So we get a non-equivariant homotopy equivalence on orbit spaces. So induced map from EG cross A mod the diagonal action on all three factors to EG cross over GA is a homotopy equivalence in the non-equivariant sense. So now we can show one of the two directions. Let X be right induced. One more time, we consider a commutative square, so we have to check that a certain map from the G-equivariant X cohomology of A to the G-equivariant cohomology of EG cross A, induced by the projection to the second factor, is an isomorphism. On the last whiteboard, I established a natural isomorphism that identifies this with the non-equivariant cohomology of EG cross G over A that uses that X is right induced, and similarly on this side we get the non-equivariant cohomology of EG cross A mod G, and this map down here is now induced by the projection to the last two factors. This is induced by a homotopy equivalence of non-equivariant spaces, so it induces an isomorphism in non-equivariant cohomology. And again, we have a commutative square where 3 out of the 4 maps are isomorphisms. So this is an isomorphism. This is one of the two implications. If X is right induced, then all these maps are isomorphisms in equivariant cohomology. So now we have to prove the reverse direction. Now let X in the global stable homotopy category satisfy the property that this map is always an isomorphism. The claim, again, we have a candidate right-induced thing for which we can compare this. In this case, we forget and then we right-induce, so we consider the unit of the adjunction. Let eta from X to right-induced of underlying of X be the unit of the adjunction. Now of the RU adjunction. And we're going to show that this unit of the adjunction is the global equivalence. We will need one ingredient that I will separate out as a claim, namely that the orthogonal spectrum sigma infinity plus L of V blank cross over G with EG is left induced. So of course, in general, if I put an arbitrary G space here, I'm not going to get a left-induced spectrum. But here I'm putting a very special G space here, namely a free GCW complex. And more generally, what happens is that if I put a free GCW complex here, then I get a left-induced spectrum. So let's prove this claim. This is a good opportunity to actually use the criterion for left-inducedness that we have established before. So we want to check that the geometric fixed point homotopy groups are constant. Now G is already taken, the notation, so let me consider the K equivariant fixed point homotopy groups of this orthogonal spectrum. So equivariant homotopy groups commute with suspension spectra. So these are just the non-equivariant stable homotopy groups of the suspension spectrum with a disjoint base point added. Now I have to take the underlying K space of this and take K fixed points of that. What is the underlying K space? Well, I get that by plugging in a complete K universe in the free variable. This is now a G times K space, the G action from here, the K action from there, cross over G with EG. And then I have to take K fixed points of this space, and the non-equivariant stable homotopy groups of this non-equivariant K fixed point space are the geometric fixed point homotopy group of this orthogonal space. Now we exploit something that I've used a bunch of times before. Before we divide out the G action, we have a commuting G and K action, and the G action is free, and then we had a formula for the K fixed points of the G orbits. So here's the formula. LVUK cross over G, EG, and then K fixed point. The general formula decomposes this as a disjoint union over contraclastic classes of homomorphisms from K to G. And then I have to take L, V, U, K cross EG. Then I have to take fixed points by the graph of this alpha. Alpha is a representative in the conjugacy class. I take the graph, that's a subgroup of G times K. I take the fixed points, and then I have to divide out the centralizer of alpha. But now something special happens, because here we have a free G action. The graph fixed points will always be empty unless alpha is the trivial homomorphism. As soon as there's an element of G in the image of alpha that's not the identity element, we can't have any fixed points here because the action on this one is free. So in this big disjoint union decomposition, there's actually only a single summand, namely the one corresponding to the trivial homomorphism. And for the trivial homomorphism, we get K equivariant maps from V with a trivial K action, but still with the G action that it comes with, into UK, and then cross EG. Because alpha is trivial, this has the trivial K action, and then we have to divide out by the centralizer. But for the trivial homomorphism, the centralizer of the image is everything, so we just get this out, and this is simply a model for BG, because this is a contractible space with some G action, and this is a free contractible space, so we get out BG. And now you can see that this is independent of whatever K was. The K-geometric fixed point homotopy groups are always the non-equivariant stable homotopy groups of the unreduced suspension spectrum of BG, independent of K. Of course, for a proper proof, you would have to check that this particular map always induces an isomorphism, but I'll omit that. And this concludes the verification of this claim that this particular orthogonal spectrum is left-induced. And the argument showed that we didn't actually have to have EG here. It would have been enough to have a free GCW complex. We are considering an orthogonal spectrum X such that the equivariant cohomology theory doesn't see you when you take product with an EG, and we still have to show that such an X is right-induced. Our strategy is to just use the adjunction unit for the RU adjunction, whose target is right-induced, and to show that this is a global equivalence. And now we have to put all the results that we proved above together. So first of all, we have to use a bunch of isomorphisms. The G equivariant zeroth cohomology of EG is by the adjunction between the forgetful functor from global to G equivariant and its left adjoint. This is isomorphic to morphisms in the global stable homotopy category from this global space, or its unreduced suspension spectrum, G, EG into X. Now I just showed that this is a left-induced global homotopy type, and if it's left-induced, then it's left-induced of its underlying spectrum. So this is left-induced of the underlying spectrum of sigma infinity plus, well, what do I have to put here? The underlying spectrum of this is just the unreduced suspension spectrum of BG. That's also what we showed on the last board. And BG is the same as the underlying non-equivariant homotopy type of the global classifying space of G. So this is left-induced also of the underlying spectrum of the global classifying space of G, because when I sort of forget, it doesn't matter if I took global or constant here. Now I'm going to use both adjunctions. I'm first going to use the adjunction between L and U to put the L over to that side and turn it into a U. Afterwards, I'm using the adjunction between U and R to turn the U over into an R on the other side. And together they give me a natural bijection where the source is now unreduced suspension spectrum of the global classifying space of G, and the target is RU of X. So now we put this together into commutative square again. So we consider the following commutative square. So here I have pi 0 G equivariant of X. Then I have pi 0 G equivariant induced by the adjunction unit here, going to pi 0 G equivariant of R U of X. So this here is also by the representability, pi 0 G equivariant R U of X. So I can plug in this chain of natural isomorphisms to X 0 G of EG, and this is just another name for X 0 G equivariant of a point. And this map down here is induced by the projection from EG to the point. So we've assumed that this projection is an isomorphism in equivariant cohomology theory. We've even assumed this for an arbitrary G space A, but in particular we know it when A is just a point, so that means that this map is an isomorphism. And again, 2 out of 3 are isomorphisms, 3 out of 4, so we can conclude that this is an isomorphism. This was the argument for zero-dimensional equivariant homotopy groups. In integer gradings, it's essentially the same, and altogether this proves the claim that the adjunction unit is a global equivalence. So X is isomorphic in the global stable homotopy category to an object in the image of the right adjoint functor, and so X is right induced, as we wanted to show. Let me add a few words about the homotopy group global functors that arise from right-induced spectra. For this, we consider a non-equivariant cohomology theory on spaces, which is always represented by a spectrum. So we consider a non-equivariant cohomology theory. Represented by some spectrum, which for us could be an orthogonal spectrum, but we really only need an object in the non-equivariant stable homotopy category. And so what does this mean? The cohomology theory, E upper 0 of X, is then by definition morphisms in the non-equivariant stable homotopy category from the unreduced suspension spectrum of X into E for X is space. So this is a contravariant functor in X. It sends cofiber sequence to non-exact sequences. It sends coproducts in X to products. So it's a cohomology theory. Because it's contravariant in X, we can now plug in non-equivariant classifying spaces of compact Lie groups. So the composite. So here we have the homotopy category of spaces. Here we have E upper 0, so this is a contravariant functor to abelian groups. And we can get a functor from red op in here. So this was the category whose objects are compact Lie groups, and the morphisms are conjugacy classes of continuous homomorphisms. And here we get a functor by sending G to BG. This is functorial for continuous homomorphisms. For example, if you use the bar construction to construct a BG, so it goes from op here to op here, and then alpha from K to G is sent to B alpha, which is a continuous map from BK to BG. And then the cohomology theory is contravariant, so we get a red abelian group. So this is half, or if you want, 2/3 of the data of a global functor. We have abelian groups at every compact Lie group. We have restriction homomorphisms. For a global functor, we would also have to have transfers, and these transfers are given by the Becker-Gottlieb transfers. For a closed subgroup H of a compact Lie group G are stable maps, stable morphisms. Let me just write it THG from the unreduced suspension spectrum of BG. This is all non-equivariant to the unreduced suspension spectrum BH. Here's a reference to the original paper by Becker and Gottlieb, where they are constructed, and the construction also involves things that entered into the construction of our equivariant transfers, like choices of representations where G mod H embeds. And because this functor is a cohomology theory, it will secretly factor over the stable homotopy category, and that means that these transfer maps induce additional functoriality in the other direction. So the upshot is that this extends the rep functor to a global functor, for which I want to write E0 underlined from the global Burnside category, an additive functor from the global Burnside category to the union group. So we're exploiting here that cohomology theories have functoriality not just for unstable maps, but actually for stable maps. Of course, to really have a global functor, if you give it in this presentation by what the restriction maps and the transfer maps are, there's a bunch of properties that need to be verified, some of which are easier than others. So, for example, you have to check that these Becker-Gottlieb transfers are sufficiently transitive, that they commute with inflation, and this is not completely trivial, you have to check the double coset formula for transfers and restrictions to subgroups. This is actually historically the first place where the double coset formula in compact Lie group situations comes up, and this was originally done in this paper by Mark Feschbach, where he verifies the double coset formula, what we can now consider as global Borel cohomology theories, which is exactly an instance of this situation. So now we go back to this right adjoint, R, from the non-equivariant stable homotopy category to the global stable homotopy category. So it takes this non-equivariant spectrum to a global spectrum, and on the last whiteboard, in the proof of the characterization, I produced an isomorphism between pi 0g of Re and E0 of Bg, and you can now wonder if this identification is compatible when the group G varies with restriction and transfer maps, and it is, and these isomorphisms constitute an isomorphism of global functors between pi 0 underlined of the right induced spectrum and this global functor that I called E underlined upper 0. So why am I bringing this up? Well, this construction, this E upper 0 underline construction, is a way without equivariant homotopy theory to produce global functors. We just needed a non-equivariant homotopy theory that we evaluated at non-equivariant classifying spaces. This produces a global functor. But from our perspective, this global functor is realized by the right-induced global homotopy type on pi 0 underlined. The last topic I would like to touch upon today is a connection between the unit of the RU adjunction and things that are sometimes called bundling maps and completion theorems. So here's the slogan for what's coming in the rest. So in special cases, the adjunction unit from X to RUX for special global homotopy types X induces things that go under the name of bundling maps. And in even more favorable cases, the cohomology theory, the equivariant cohomology theories represented by Ux can be obtained from those of X by completion theorems. So more precisely, I will discuss two examples in detail. One is the global K-theory spectrum, which will have to do with the Atiyah-Segal completion theorem. And I will also discuss the global sphere spectrum from this perspective. And there we'll have Carlsson's theorem, which affirmatively resolves the Segal conjecture. So here's the first example. So this needs the global K-theory spectrum. Which I denote by Ku, and in the written sources it would be boldface Ku. And this is a commutative orthogonal ring spectrum, or what I like to call an ultra-commutative ring spectrum. It's due to Michael-Joachim. That represents equivariant K-theory. It represents equivariant K-theory for compact Lie groups G in a way I will recall in a second, but it's actually a global object. The actual definition of this is concrete, but it involves things that I haven't talked about. It involves spaces of Z2 graded C star algebra homomorphisms. These are things a little bit further away from what I would usually discuss, so I decided that I'm not going to give you the actual definition here. I'll just give you the reference to the original paper by Michael-Joachim and also where this is discussed in the Global Homotopy Theory book. Still, I want to give you some of the key properties for a compact Lie group G and a finite GCW complex. There's a specific isomorphism that you can find in the Global Homotopy Theory book. Between K, G of A and the zeroth G equivariant cohomology theory represented by A. So this side we have already discussed. That's the cohomology theory represented by a global stable homotopy type. And this is the Grothendieck group of isomorphism classes of G vector bundles over A under Wigner sum. These natural isomorphisms are not only natural in the G space A, both sides are contravariantly functorial on A. They're also natural for restriction maps in G. You know, if you have a continuous homomorphism, you can restrict in G and you can also restrict the action along A, and they're compatible with that. So moreover, in the special case, when A is a point, then this specializes to isomorphisms so then we have Kg of a point isomorphic to K U G equivariant 0 of a point. But this is, well, it's not the same, but it's canonically isomorphic to the complex representation ring of G, because vector bundles over a point are just G representations, and this is just a different name for pi 0 G equivariant of Ku. And then in this special case, these isomorphisms are also compatible with transfers. This is not a completely obvious thing in general. It would be substantially easier if we restricted our attention to finite groups only. You know, here the transfers are the homotopy theoretic transfers. On this side, on the representation rings, these are the representation theoretic transfers. So for finite groups, or more generally when we have a subgroup H of finite index in G, then you can induce up a representation. The dimension goes up by the index of H in G, and so this is really induced by something on isomorphism classes of representations, and it's compatible with direct sum, and it passes to the Grothendieck group. However, on this side, we also have the transfers where H has a smaller dimension than G, but it has finite Lie groups. Here they are homotopically theoretically defined. And on this side, the transfers are the smooth induction, first introduced by Segal, and they involve some analysis. And they're also more complicated because the smooth induction, if you plug in a class represented by an actual representation, then the smooth induction might take this to a virtual representation. If we believe all this, then it follows from this that there is an isomorphism of global functors. There is an isomorphism of global functors given by these isomorphisms between the complex representation ring global functor and the homotopy group global functor of the global K-theory spectrum. This particular K-theory spectrum, this global K-theory spectrum, is the periodic version, so it satisfies spot periodicity, and this comes out as follows. The spectrum, the global spectrum, ring spectrum Ku is spot periodic. i.e., there is a unit beta in pi 2 non-equivariant of Ku. Because you have a unit in the non-equivariant graded homotopy ring, and because this is a global spectrum, all the equivariant theories will also be two periodic, because we can always apply inflation from the trivial group to any other compact Lie group. Inflation is an example of a restriction homomorphism, so that gives a homomorphism of graded rings. So if we inflate this unit in the non-equivariant ring to a compact Lie group G, we get a unit in degree 2 of the graded homotopy ring for every compact Lie group G. So all the G theories are actually about periodic, which of course we could also have deduced from this isomorphism, or at least if we believe that can be extended to arbitrary integer gradings. Another piece of information is that in the odd degrees, all the equivariant homotopy groups for all compact Lie groups actually vanish, so this is concentrated also equivalently in all the even degrees. The global K-theory spectrum is not right-induced. After all, equivariant K-theory is different from non-equivariant K-theory of the Borel construction. But it would be a shame not to mention at this point that it is right-induced in some relative sense. So the global K-theory spectrum is right-induced from the global family of finite cyclic groups. So this doesn't quite make sense from the things that I have explained here. To really give meaning to this, you'd have to believe that there's a relative version of global homotopy theory where you start with some family of compact Lie groups that's closed under passage to subgroups and quotients. The finite cyclic groups are an example of such a family. Other interesting families would be all finite groups, or maybe all abelian compact Lie groups. And then there's a version of global homotopy theory where you test equivalences only on the equivariant homotopy groups in this family, and all the general theorems that I've discussed so far have analogs. In particular, there will be a restriction functor from the full global stable homotopy category to the global stable homotopy category based on some family of compact Lie groups, such as the one based on the finite cyclic groups. And this restriction functor will again have both adjoints, and both adjoints will be fully faithful. So this is not to be confused with a restriction functor to G equivariant homotopy for one fixed group. We are restricting to a family and doing a global theory for a family. And in that situation, the restriction functor from the full global to the global with respect to some family has both adjoints, and they're both fully faithful. And what I'm saying here is that this global K-theory spectrum is in the image of this relative right adjoint, which starts from the global theory based on the family of finite cyclic groups. In the end, where this all comes from is the fact that representations are detected by characters. So because the global K-theory spectrum is not right-induced in the full sense from the non-equivariant stable homotopy category, we can consider the adjunction unit. Eta from Ku to the right adjoint applied to U of Ku. So U of Ku is just a non-equivariant model for periodic complex topological K-theory. So this is not a global equivalence. It's not an isomorphism in the global stable homotopy category, but you can say a little bit more about it. So for G is a compact Lie group, You can evaluate this on zeroth equivariant homotopy groups. So we get pi 0 G equivariant of eta from pi 0 G equivariant of Ku. I told you on the last whiteboard that this is isomorphic to the complex representation ring of G. This goes to pi 0 G equivariant of Ru of Ku. And this is isomorphic to the non-equivariant zeroth K-theory of the non-equivariant classifying space of G. So the junction unit gives a map here. And of course, since I haven't told you various identifications, it is not completely meaningful right now here, but the thing to check and the interesting thing to check is that under all this is identification. This sends the class of an actual representation to the class of the vector bundle EG cross over G with B to EG mod G, which is DG. So a representation of the group G has an associated vector bundle over BG. And that's what this map does, what the junction unit does on equivariant homotopy groups under suitable identifications. I guess this is the reason that maps of this kind are sometimes called bundling maps, because it sends a representation to the bundle associated with the representation. Now this map is in general not an isomorphism. This is not a right-induced homotopy type, but there's a famous theorem, and that's the Atiyah-Segal completion theorem. And it says that for every compactly group G, the map that, of course, previously was directly given in terms of this construction, but that we can now reinterpret as the effect of the adjunction unit on equivariant homotopy groups, going to Ku0 of Bg, is completion at the augmentation ideal. So what is the augmentation ideal? Let me write IUG for it. It's just the kernel of the dimension homomorphism, which goes from the complex representation ring to the integers, and it assigns to a virtual representation its virtual dimension. So you can also put this in slightly different words. So this abelian group here is already complete with respect to the filtration given by the powers of this augmentation ideal. This is not complete, but if you extend this to the completion, it becomes an isomorphism. There's a slightly more general form of this Atiyah-Segal completion theorem. More generally, you could consider the G-equivariant K-theory of a finite GCW complex and map that to the non-equivariant K-theory of the homotopy orbit construction. That map, again, is not an isomorphism, but it becomes an isomorphism if you complete the source at this augmentation ideal. There's another celebrated completion theorem that I would like to mention in this context. This was originally known as the Segal conjecture, and it was eventually proved by Gunnar Carlsson. From our perspective, this arises from the global sphere spectrum. The junction unit of the global sphere spectrum going to the right adjoint applied to the non-equivariant sphere spectrum induces maps of cohomology theories. On the one hand side, we have the pi 0 G equivariant of A, so this is the G equivariant stable cohomotopy. G equivariant stable cohomotopy. And on the other side, after using the identifications that we've done with the cohomology theory of a right-induced spectrum with the homotopy orbit construction, this goes to pi 0 stable of the homotopy orbit construction of EG cross over G. Okay. And then the theorem that's due to Carlsson and that was previously known under the name Segal conjecture says that for finite groups G and finite GCW complexes A, This map up here is also a completion map at the augmentation ideal. Now it's a different augmentation ideal from the case, in the K-theory case, there we had the representation ideal, and this is the augmentation ideal. I of G is now the kernel of the map from the Burnside ring to Z that counts the virtual cardinality. Again, this sort of means that this side is already complete for that ideal, this side is not, but if you complete it, the map becomes an isomorphism. In this completion theorem, the finiteness is essential here, not just the finiteness of the GCW complex, also the finiteness of the group. This is not true as stated for compact Lie groups in general. There are also additional complications that come up in the compact Lie case. So for example, EG is really an infinite GCW complex, and in the finite group cases, this theory is actually the same as the inverse limit of the theories you get by filtering the EG via Skeletor, but in the compact Lie case, these two things are different, and there's all sorts of additional complications. So here's a reference to a survey article where you can find out what's known about this kind of question in the generality of compact Lie groups. So I've brought these things up not because the global perspective actually helped in the proofs of these theorems, the Atiyah-Segal completion theorem and Carlsson theorem, also known as the Segal conjecture. These theorems are older than the global formalism. In the proof, global kinds of elements enter because in both of these theorems there are some reduction steps that reduce the general case to the case of special kinds of, in the one case, would be from unitary groups and then eventually to tori, and in this case to P groups and then down to the cyclic group with P elements eventually. So there are all sorts of reduction arguments that use the global structure, in particular transfers, but the really hard work is not something that the global formalism makes any easier, and of course these results are older and they predate the global formalism by quite a bit. Nevertheless, I brought these things up because I think on a conceptual level it is quite nice to see that at least the maps are just special cases of something very general. If you have an interesting global homotopy type, it has this unit of the adjunction that will induce a map from the equivariant cohomology theory to the cohomology theory of the Borel construction. And this is a global map. It's really defined on the global level. It's simultaneously defined for all compact Lie groups compatible with all the global structure. So I'm hoping that this might be useful in formulating this kind of completion theorems in general. This is all I wanted to say today. In the next lecture, I will turn to the standard T structure on the global stable homotopy category, which will eventually also lead to the construction of Eilenberg-MacLean spectra for global functors. This is all for today, and I thank you for your attention.